So application of stack. What is the application of stack? Recurrence. Recurrence is the application of stack, main application of stack. So in the recurrence, we have to learn the Tower of Hanoi problem, Quicksort, and another application, that is postfix evaluation. Infix to postfix conversion. This is uh, this program, infix to postfix conversion, is kept in the beyond syllabus bucket. Okay, so we will discuss this later, that is the conversion, infix to postfix beyond syllabus. This will be discussed later. So today we will discuss about the Tower of Hanoi, the Quicksort, and the postfix expression. So Quicksort, let us start with the Quicksort. So first of all, is it visible?
Yes, sir.
Okay. Please respond. So Quicksort is a divide and conquer approach. It depends upon the divide and conquer approach. Okay. So Quicksort means you have to sort unsorted array, right? So this particular problem, Quicksort, it depends upon the divide and conquer approach. What is divide and conquer approach? Divide and conquer. Do you know what is divide and conquer approach? Any idea about divide and conquer? Anyone?
Sir, each time we'll divide the array and then proceed on
Yes.
either half.
Yes. So every time, if n is the size of the problem, if n is the size of the array, then we have to divide this. The general step is we have to divide the array in b sizes so that each subproblem will be of size n by b. Okay. In case of binary search, we divide the array in equal to halves. Okay. So every half will be of size n by 2. Here the value of b is 2. Okay. Now this is the divide and conquer approach. Binary search depends upon divide and conquer approach. That's why we have to divide the whole array into two parts. In general, b parts. That is, each subproblem will be of size n by b, and recursively we have to solve the subproblems. Just remember that recursively we have to solve the subproblems. So this is the application of recursion. Okay. Now, just 1 second. So recursively we have to solve the subproblems, and finally, that is, we are conquering our problems. We have to first divide the problem into b subproblems. Then we have to conquer, that is, solve the problem, and finally we have to combine the subproblem result so that we can get the final result. Okay. So what is the recurrence relation for binary search? Do you know what is the recurrence relation? From that recurrence relation we can get the complexity of the algorithm, the complexity of the binary search algorithm. What is the complexity of binary search algorithm?
LGN.
LGN. Okay. So order of log n. Order of log n. This is the complexity for binary search. But what is the recurrence relation for binary search? Any idea? Any idea?
+1.
Tn. So n is the problem size and Tn time taken for solving the problem with size n. So Tn is equal to
Tn by 2 +1.
Okay. So here in the left part, the size of the, here in the left part, your size is n. in right part you are dividing the problem in two halves. That's why T of n by 2. Okay. And in case of binary search, we are discarding the other half. Okay. That's why we have to deal with only one part. We have to deal with only one part. So 1 into T of n by 2 plus here the total function is 1 constant. Why constant? Because we are dealing with only one element, the search element. Okay, that's why the total function fn is here 1. This total function fn, actually the formula, actually the form is t of n is equal to a into t of n by b, a into t of n by b plus fn plus fn. So this is the general format. So there are a number of subproblems and each subproblem has size n by b, and fn is your total function. What is fn? Fn is the cost function. Okay, so cost function for division of your problem into into a number of subproblems. Each subproblem has size n by b, and you have to recursively solve the subproblems, and finally you have to combine the subproblem result so that we can get the final result. Okay, so this is the fn. This is the actual physical meaning of your fn. In case of binary search, as you are dealing with only one element, that's why your uh, that's why the combining your final result will take the constant time. That's why here fn is 1. Okay, so this is the recurrence relation for binary search. So if you use the substitution method, any recurrence relation, please make a note, any recurrence relation can be solved in 3 ways, in 3 techniques. For solving a recurrence relation, we can use 3 techniques. First one is the substitution method, second one is the recurrence tree method, third one is the master theorem. So if you use any of the 3 methods, we can get the time complexity for this particular algorithm order of log n, that is lg2 base n. Okay, lgn. Now in case of Quicksort, do you know what is the time complexity for Quicksort? Any idea? Anyone?
Sir, not sure, but I think it is n log n.
Yes, n log n. But why n log n? So n log n, this is actually n log n is your average case and best case time complexity for Quicksort, not the worst case. Worst case time complexity is same as bubble sort, insertion sort, selection sort. That is in case of bubble, insertion, selection, the complexities for this type of sortings are order of n square. But if we use the divide and conquer approach, that is every time we can divide the array into small subproblems and recursively solve the subproblems, then Quicksort and merge sort, these two sorting depends upon your divide and conquer approach. So these two sorting will have the time complexity n log n. So the time complexity for this type of sorting is getting reduced, okay, from n square to n log n. But what is the recurrence relation for Quicksort and merge sort? Any idea? How they differ? How they differ from binary search? So Tn is the time taken for solving the array with size n. So here also it depends upon the divide and conquer. So every time you have to recursively divide 2 parts, the whole array. So each subproblem will be of size n by 2. Okay, plus every time you have to recursively divide the whole array into two parts, but two parts are required to get the final result. In case of binary search, we can discard the other part, but in case of quicksort and merge sort, two parts are necessary for getting the final result. That's why we have to put 2tn by 2. Okay, so this is the difference. Here this is 1 and here this is 2. Okay, now again, here in case of binary search, the toll function fn is constant, but in case of quicksort and merge sort, this will be n. Why n? Any idea? Can you guess why the toll function is order of 1 in case of binary search, but in case of order of n in case of quicksort? Any idea? Not getting any answer.
Sir, because this is sorting and that is binary search, so only one element.
Yes, because we have to deal, because here this is the sorting, we have to deal with n number of elements. That's why the toll function is order of n. But here in case of this is the particular searching, a searching key value, only one key value. Either this exists in the array or not. That's why this is 1. Yes, very good answer. This is 1, and in case of sorting, this is order of n. If you solve this particular recurrence using either substitution method or recurrence tree or master theorem, you can get order of n log n. Order of n log n. Okay, so this is the time complexity and recurrence relation for binary search and quicksort. Now we have to start with quicksort. So quicksort, it depends upon the divide and conquer approach. Okay, depends upon a divide and conquer approach. Okay, now this is called the partition exchange sort. Partition exchange sort. Okay, that is, we have to every time, every iteration, we have to find out the pivot. Okay, pivot element. We will discuss pivot element shortly. Every iteration we have to find out the pivot element, and we have to, our task is to place the pivot element in its proper position. Okay, then recursively we have to solve the two sub problems. So actually the placing of your pivot element will divide your whole array into two parts. Okay, so we have to search, we have to search the pivot element. Okay, here we will discuss about Lomuto partitioning. What is Lomuto partitioning? This Lomuto partitioning says that always choose the last array element as the pivot. Okay, according to Lomuto partitioning, that is, we have to partition the array every time so that the array is getting divided, it is getting reduced, the array size getting reduced. Okay, so this is the Lomuto partitioning. According to Lomuto partitioning, the pivot element is the last element. Okay, in case of Hoare partitioning, if you use the Hoare partitioning, then the first element is the pivot. But today we will discuss about the last element as a pivot. That is, we partition the array using Lomuto method. Okay, you can also use the first element as the pivot, that is Hoare partitioning. Hoare partitioning Quicksort and Lomuto partitioning Quicksort, both are same. Just pivot point selection are different. There is also randomized Quicksort. You can take any of the element from the array and you can make this as a pivot. It is also possible. Okay. So first start. Let us start with the algorithm. Up to this, any problem, please respond. Do you have any queries up to this?
স্যার এই লোমুটো পার্টিশনিংটা একবার বলবেন?
According to Lomuto, that is Quicksort is totally, first one, Quicksort is the example of divide and conquer approach. Okay. Quicksort is also called the partition exchange sort. That is, every iteration you have to partition, you have to divide the whole array. Partition exchange sort. That's why this is recursive. That's why this is recursive. Okay. Every time you have to partition the whole array. That is, recursively you have to divide the whole array. That's why this is the divide and conquer approach. Now, partitioning means we have to place the pivot in its proper position so that one part of the left part of the pivot element is less than is equal to pivot and right part of the pivot is greater than is equal to pivot. And according to Lomuto partitioning, always choose the last array element as the pivot. Okay. So first we write the algorithm. Let Quicksort and there are three arguments. Let us choose three arguments. First argument is your array name, array, and P is the first index and R is the last index. Okay. Now first, 1 second. So first, if, why this is getting bold every time? If your first index is less than your last index, this is quite obvious. Okay. Then Q is equal to, Q is a variable. Actually, Q is your pivot. That is, you have to place this Q in its proper position. So Q is equal to partition function, also P and R. Okay. Then Quicksort A, P, Q minus 1 and Quicksort A, Q plus 1 and R. Okay. That is, this line number 3 and 4 are the example of your recursive call. This is the recursive call, recursive function. Quicksort is the recursive function. Why recursive function Quicksort? This function is recursive because it calls itself, but in a smaller version. Here the array first index is P, last index is R. But here in the third line, the Quicksort calls with first index P and last index Q minus 1. Obviously, Q minus 1 is less than R. So this is the first recursive call and this is the last recursive call. Okay. Now we have to declare the part function. So part function A, P and R. Number 1, first line. First line, we have to choose X is equal to A of your last element. So actually X is your pivot. So X, Q both are same. So this X will contain the last element of the array. Then I is equal to P minus 1. I is equal to P minus 1. Next, for J is equal to P2 R minus 1. Sorry, P2 R minus 1. If AJ, if AJ is less than is equal to X, then first increment the value of I. First increment the value of I, then exchange the value of AI and AJ, AI and AJ. Okay, finally exchange AI plus 1, AI plus 1 and A of R. Okay, and return I plus 1. So this is the Quicksort algorithm.
Sir, can you please explain what is Quicksort first, by giving a small example?
Obviously,
Thank you, sir.
I will explain every step one by one. So for this and if this, this and this. So is it visible? The part function and Quicksort function. So this is the actual algorithm. In your main exam, if you are asked to find out to write the Quicksort algorithm with explanation, then you have to write this algorithm Quicksort along with the part function. Okay, then you have to explain with the example. Let us have an example. Let the array is 2 8 7 1 3 5 6 4. So this is the array. This array is given. You have to sort this array using the Quicksort algorithm. That is using this algorithm. Okay. So first of all, so this is your array A. Okay. This is your array, and this is the first index, and this is the last index. Okay. So obviously P is less than Q, P is less than R. If P is less than R, then Q is equal to, that is partition. The output of this partition function is stored in Q. Okay. And then recursively solve A P Q minus 1 and finally A Q plus 1 R. So this is your Q. Okay. So every elements in the left hand side are less than is equal to Q, and every elements in the right hand side array are greater than Q. Okay. So actually we are dividing this array in these types, that so this is your P and this is your q minus 1. This is your q. And this is your right array. So starting from q plus 1, okay, to r. So this is the divide and conquer approach. This depends upon divide and conquer approach. So we have to recursively solve the sub problem. So you have to place this pivot point. Just 1 second. Hold on 1 second. Hello, am I audible?
Yes, sir. Sir,
Yes.
shouldn't that be less than Q instead of less than equal to Q?
Less than is equal to q. Actually, this is less than is equal to q. This is greater than q. Suppose there are, suppose the array is, suppose this is the array given. Suppose the array is 4, 4. Then what will be the scenario? Megha? Then what should we do? So this 4 is the last element is your pivot. So every element less than is equal to your last element must be in the left array. Okay.
Sir, but when you have split it, you have taken Q separately.
Yes, this is just a particular pivot. This position, this particular position, this element is your last element. Suppose there are multiple elements, okay, multiple same elements.
Sir, less than Q is okay, but how can it be equal to Q if you are taking Q separately?
Actually, this is the division rule. Every elements less than is equal to every elements less than is equal to q. The left hand side must be less than is equal to q. Suppose there are multiple elements like this 4, 4, 4. There are 3 4s. Then this extreme 4 last element is your pivot element. You have to place this 4 in its proper position. So 2, 1, 3 and 2 times 4, these belongs to the left array. Okay.
Yes, sir.
Now, so you are dividing the array into 2 parts, and then you have to recursively solve the left array and right array. So line number 3 and line number 4. So this is the line number 3. In the Quicksort, line number 3. After the completion of the line number 3, only line number 4 will start. So line number 3, this is actually for left sub array. This is for left sub array, and this is for right sub array. Okay. So this is the Quicksort function. This depends upon the divide and conquer approach, and recursively we have to solve every sub problems. Up to this, any problem? Please clarify. Every time we have to place the last element in its proper position so that the left array contains less than is equal to q and right array contains greater than q. Okay. Now we have to discuss about the partition function. So this is the partition function. Okay. So let us start. What is your array? 287. So 2, 8, 7. 287. Next is 1. Next is 3, 5, 6, and 4. So this is your 0, 1, 2, 3, 4, 5, 6, 7. So this is your 7. Okay. So this is your array. So this is your array. Now, if P is less than R, quicksort function, if P is less than R, so what is the value of P? What is the value of P?
2.
Value of P is 0. P is the index. R is the index. So 0 is less than 7. 0 is less than 7. So you have to execute line number 2, 3, and 4 in quicksort function. So what is the line number 2? That is Q is equal to part of APR. Now the output of the part function will store in Q. So what is the output of the part function? So part function, line number 1, X is equal to AR. So what will be the value of X? Anyone?
4. Sir, 4.
Yes. So X is equal to 4. Why? X is equal to A of R. R is the index, not the value, not the array element. It is actually array index. So X is equal to 4. Next, I is equal to P minus 1. So I will be set here. Okay. Now J will run from P to R minus 1. So what will be the initial value of J? J will be pointing in this position. Okay. Next, if AJ is less than is equal to X, is it feasible? What will be the value of AJ? Anyone?
2.
2.
Yes. So value of AJ is 2 because in the first iteration J runs from P index, that is 0th index. So AJ value of AJ is 2. Now AJ is less than is equal to last element X 4. Is it true or false? True. Oh. Then what should we do? First increment the value of I, then exchange the value of AI and AJ. Okay. So first increment the value of I. So I will be now at this position. Okay. And then exchange AI and AJ. So 2 is exchanged with itself. Is it clear? Up to this? Please ask me. Not getting any answers from you. Ishita,
Yes, sir.
is it clear?
Yes,
The
sir.
execution?
Yes, sir.
Okay. Then what is the next step? Your next step is increment the value of J coming out from the loop. You have to increment the value of J. So what will be the value of J? New value. So J will be now at this position. Now you have to check again. Line number 4. If AJ is less than is equal to X, that is, what is the AJ value?
8.
8 is less than is equal to 4. No, false. This is false. So don't enter in the if block. Okay. Next, again, you have to increase the value of J. Again, increase the value of J. So J will be now at this position. So 7. Now you have to enter in the if block. You have to check the condition. If AJ is less than or equal to X, that is 7 is less than or equal to X, value of X is 4. 7 is less than or equal to X. No, false. Don't enter in the if block. Rather, increase the value of J. So J is equal to now AJ. What is the AJ value? 1. 1 is less than or equal to 4. It is true. What should we do? Any idea what should we do?
Sir, I will become
Type
1.
So first increment the value of I and then exchange AI and AJ. So first increment the value of I. So I will be now at this position and then exchange the value of AI and AJ. So then exchange AI and AJ. Okay. So this will be your 1 and this will be your 8. So this is 1 and this is 8. Is it clear?
Yes, sir.
Okay. So coming out from the loop, you have to again increase the value of J. So increase the value of J. So J is now at 3. So 3 is less than 4. Yes, true. Then we have to again increase the value of I. Okay. First increase the value of I and then exchange AI with AJ. So exchange AI with AJ. Okay. So this will be your 3 and this will be your 7. So this will be your 3 and this will be your 7. Next, increase the value of J. So 5 is less than is equal to 4. No, false. Don't enter in the loop. Increase the value of J. So J will be at this position. So 6 is AJ is check whether AJ is less than 8. That is 6 is less than 4. False. So this will be your stop location because this is R minus 1. Okay. J will stop at this position. Now what should we do? Any idea? This is the stop of your loop. Ishita, what
Yes,
should
sir.
we do? What should we do now?
So get back to the quicksort function.
No. Line number 7. Exchange AI
Oh,
plus 1 with AR. Line number
okay.
7. AI plus 1 with AR. So what is the AI plus 1? What is
8.
the AI plus 1?
8.
So 8. So 8 is replaced with AR. Okay. So just this will be your 4 and this will be your 8. So this is the pivot element placement according to the Lomuto partitioning. Choose the last element as the pivot and place that pivot in its proper position so that we can divide the whole array into 2 parts. One part is less than is equal to 4. One part is less than is equal to 4 and other part is greater than 4. Okay. Other part is greater than 4. So this is the division. Then again you have to recursively solve the problem. 2, 1, 3. 2, 1, 3. Megha?
Yes, sir.
So 2, 1, 3. How to solve this 2, 1, 3? So this is the, so this 4, placement of this 4, placement of this 4, this placement of this 4 in its proper position, that is completion of your second line, completion of the second line. Now we have to solve recursively the third line and fourth line. So third line, we are now going to solve the third line. So 2, 1, 3, 2, 1 and 3. How to solve 2, 1, 3? Any idea, Megha?
Sir, P will be 0
Okay,
and R will be 2.
okay. This is quite obvious then. So this will be your I and this will be your J. Then what should we do?
Sir, since 2 is less than equal to 3, I will become
Every time you have to check whether AJ is less than is equal to X. So here the X value, what is X? X is equal to AR. So here X is equal to last element. So 3.
3.
So 2 is less than is equal to 3. Yes, this is true. So increment the value of I. So increment the value of I, then exchange. So then exchange AI and AJ. So 2 is replaced with itself. Okay.
Yes, sir.
Then increment the value of J. Then Megha, 1 is less than or
1
equal to 3.
equal to 3. I
Then
becomes
I becomes,
1.
so increase I, and then
1 will be replaced with itself.
sorry, 1 will be replaced with itself. Then
Then stop the loop.
why stop the loop?
Sir, till R minus 1 it has to run, na?
R minus 1. So stop the loop. Then what is our task?
So find the pivot point, that is I plus 1.
No. Exchange AI plus 1 with AR. Line number
Yes.
7.
Yes, sir.
So I plus 1. So AI plus 1. What is the value of I plus 1?
2.
So AI plus 1 means 3.
Yes, sir.
Yes, AI plus 1 means 3. So 3
Yes.
is exchanged with AR. That is 3 is replaced with itself. Okay.
Yes, sir.
So actually this 3 is placed. So your pivot element is placed in its proper position. Look
Yes, sir.
carefully. So every element in the left array are less than is equal to 3. Okay.
Yes, sir.
Now 2, 1. You have to solve this 2, 1. How to solve this 2, 1? So this is your P and this is your R. This is your I and this is your J. Okay. Now, what is the value of X? Here the value of X is
1.
last element 1. So you have to check whether AJ is less than is equal to X. So 2 is less than is equal to 1. False?
Yes, sir.
This is
False.
And obviously this is your R minus 1, R minus 1. So you have to stop this J, loop of J.
Yes, sir.
Okay. Now we have to exchange A of I plus 1. A of I plus 1 with A of R. That is 2 is exchanged with 1. So you can get 1, 2.
Yes, sir.
So 1, 2, then 3, then 4. 4 is placed already. And then 7, 5, 6, 8. You have to solve 7, 5, 7, 5, 6, 8. 7, 5, 6, 8. So this is the completion of the third line. After the third line, we can get this scenario. 1, 2, 3, 4, 7, 5, 6, 8. Is it clear? This is the quicksort algorithm. Any queries, please ask me. Muskan,
Yes, sir.
is it clear to you?
Yes, sir.
So this is the partition exchange sort or quick sort using the Lomoto partitioning. You can also use the first element as the pivot using Horde partitioning. Here we choose the last element as the pivot. Okay. So the average case and best case, the average and best case. Best case behavior is order of NLGN. But the worst case, behavior is order of n square. Mind it. Order of n square. Why order of n square? What is the worst case behavior? This is the interview question. What is the worst case behavior? Many times from GATE this question arises. What is the worst case behavior of quicksort? That is, worst case behavior means your array is already shorted. Your array is already shorted, either in ascending or descending. So then the worst case scenario will be in the form order of n square. Okay. So average case and best case scenario is order of n square, order of n log n, and worst case complexity is order of n square, where n is the input size. So this is the quicksort algorithm with explanation. Okay. Just 1 second. So this is the quicksort function. Is it visible?
Yes, sir.
So this is the quicksort function. I'm just writing the quicksort function from this algorithm. Quicksort APR. So quicksort APR. Here also quicksort int A, your P and R. And if P is less than R, then partition function will be executed and the result is stored in integer q. Okay, we have to place the q in its proper position. Then line number 9 and 10, that is recursive call of quicksort, but first apq minus 1 and aq plus 1 are. So here this is equivalent to line number 3 and 4. Okay, next partition function. So partition function means partition function. So this is the partition function. Here last element is stored in x. So x is equal to ar, I is equal to p minus 1, and j runs from p to r minus 1. So if aj is less than is equal to x, so aj is less than is equal to line number 4. Line number 4 is aj less than is equal to x. Then first increment the value of I, then exchange, that is swap. So first increment the value of I, then swap AI and AJ. Okay. And finally, this is the closing of the for loop. So this is the closing of the for loop, and closing of the for loop, we have to call the exchange, that is swap AI plus 1 with AR, and finally return the I plus 1. So here swap AI plus 1 with AR and finally return the I plus 1. Okay, so just writing this. 1 second, what is this? So enter the number of elements in the array. So what is the number of elements? Here the number of elements is in our example 8. Okay. So 1 by 1, 2. Next is 8. Next is 7. Next is 1. Next is 3. Oh, 5, 6, 4. So is it visible? The before sorting the array is this, and after sorting this is the array. Okay. Do you have any queries regarding the quick sort? This is the algorithm. This is the algorithm for quick sort and partition function. And this is the step-by-step pictorial description. This is the recursive definition of the quick sort, that is Tn is equal to 2Tn by 2 plus n, total function n. Finally, we get the complexity. Actually, this is the average case or best case complexity order of n log n. But for worst case, if the array is already sorted, then the complexity is order of n square. Okay. Any queries? Megha, is it clear?
Yes, sir.
Okay. Now we have to learn about the Tower of Hanoi. Do you know what is Tower of Hanoi? Any idea? Already discussed in your previous semester. Any idea about Tower of Hanoi? This is another example for recursion. Anyone? Megha, do you know what is Tower of Hanoi? Tower of Hanoi problem?
Yes, sir. There are discs, and we have to arrange them in ascending order.
In descending order, there are
Like
three.
the
There are
smallest on top and the biggest at the bottom.
yes. So A, this is your B, and this is your C. What is the complexity for Tower of Hanoi? What is the time complexity for Tower of Hanoi?
So 2 to the power
Sir,
n.
e to the power x.
E to the power x?
2
No,
to the power n.
2 to the power n. Okay. Now, Kishan, what is the recurrence relation for Tower of Hanoi?
Sir, don't know, sir.
Okay. So first start with Tower of Hanoi. Just 1 second. Tower of Hanoi. We are just writing the move. Okay, move. So let first argument is the number of disk. Second argument is your source and your actual destination and auxiliary peg or tower. Okay. Now move. So this will be your int move. Oh, sorry, int n. Then let your source is character, and this is your character destination, and this is your character auxiliary. Okay. Now if there is only one disk, if there is only one disk, that is single disk, just write down move from source to destination. Okay, source to destination. So source to destination. Okay. So this is the if x is equal to 1. Otherwise,
Sir, what is X?
sorry, it will be n. Very good. If n is equal to 1, that is number of disk is 1. If the number of disk is 1, then move from source to destination. Otherwise, that is there are more than one disk. Any idea? There will be three functions, three recursive functions, three recursive calls. So first call will show that move the n-1 disk from the source to the auxiliary using the destination. Okay. Next move the only one single disk, that is the largest disk, resides at the source. So from source to your actual destination using the auxiliary. The last argument is your using the auxiliary. Okay. And next, what should we do? Next, what is the first argument? Number of disk. So number of disk is n-1. Okay. Then from which?
From auxiliary.
Yes. So from auxiliary to the actual destination using the source. So this is the move function. So in the there will be three recursive move functions. Okay. So in the first move there will be n-1 disk. Second move there will be one disk. Third move there will be again n-1 disk. So what is the recurrence relation? So if you write Tn as the time taken for movement of n number of disks, then at the first move, how many disks are replaced? At the first move, first recursive call, how many disks?
n-1.
T of n-1. In the second call,
1.
there is 1. In the third call,
n-1.
T of n-1. Okay. Is it clear? So, if you add 2t n-1, 2t n-1 plus t of 1. Here the time taken for movement of one disk is always constant. Here we choose, this is our assumption. So t of 1 is 1. Okay. So this is the recurrence relation for tower of Hanoi. Tn is equal to 2tn-1 plus 1. So this is the recurrence relation. Is it clear? Is it clear to you?
Yes, sir.
Yes, sir.
Now you have to solve this recurrence relation. You have to solve this recurrence relation using substitution method or recurrence tree, because master theorem can't be applied in this scenario, because there is a form for application of master theorem. Master theorem can be applicable only for the recurrence relation with the form Tn is equal to Atn by B plus Fn. Okay. Now, what is the substitution method? Any idea? Do you know what is the substitution method? Any idea?
No, sir.
Megha, do you know what is substitution method?
No, sir.
Okay. Substitution means you have to substitute the value. That is, here you have to substitute this t of n-1 in the form of Tn. So we can write 2. T of n minus 1. If you place T of n minus 1 in the LHS of the equation, then you can write this as 2 of T of n minus 2. Okay? Plus 1. Can we write that? So we just substitute the value of Tn in the form 2Tn minus 2 plus 1. Is it okay, Kishan?
Yes, sir.
Then you have to again substitute the T of n minus 2. So 2 of T of, what will be the value? Next value. Any idea?
N minus 3.
So n minus 3. So n minus 3 plus 1. N minus 3 plus 1. Okay. Again plus 1.
Again plus 1.
Plus 1. Now if you solve, just write down. This will be 2 to the power 3. 2 to the power 3 T of n minus 3 plus 2 square plus 2 plus 1. Okay. Now 2. What do you mean by 2? What do you mean by 2? 2 to the power 1? We can imagine this as 2 to the power 1. And what is 1? What is 1? 2 to the power
2 to the power 0.
Yes, 2 to the power 0. So 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Okay. So from this we can get 2 to the power n minus 1 after the n minus 1 step. So 2 to the power n minus 1. So n minus 1. Okay. Plus. What will be the value? Next value? 2 to the power n minus 2 plus up to 2 plus 1. Is it clear? Is it clear to you? So, Megha, 2 to the power n minus 1. 2 to the power n
Sir-
minus 1, 2 to the power 1. Sorry, T of 1.
Sir, where you have written 2 cube T n minus 3. Sir, in the previous step you have written n minus 3 and again in the next step you are writing n minus 3. Shouldn't it be n minus 4?
No, I'm just rearranging this step.
Okay. Okay.
So 2 to the power n minus 2. So Megha, what will be the formula?
Huh?
What will be the formula?
No, don't know, sir.
So T of 1. What is T of 1? T of 1 means 1. Okay.
Yes,
This is
sir.
assumption. T of 1 is 1. Now, this is the GP series. A into R to the power n, A into R to the power n minus 1 by R minus 1. Okay. So what is A? First term. First term is your 1. And what is common factor? Here the common factor is, what is the common factor? Yes, 2. So 2 is the common factor. So finally, we can solve this as 2 to the power n minus 1. Because 2 minus 1, the denominator is already 1. So 2 to the power n minus 1. So we get Tn is equal to 2 to the power n minus 1. What is Tn? Tn is the number of movement. So number of movement will be 2 to the power n minus 1. If n is 3, There are 3 disks. If n is 3, then how many movements are required? This is the
7.
very, yes, 7. This is a very good question. How many moves are there if the value is n is equal to 4? Then you have to apply 2 to the power 4 minus 1. Okay? So this is the formula. Number of movement. Now, what will be the complexity for this tower of Hanoi? You can easily omit. You can easily omit the constant part. Okay? You can easily omit the constant part. So that's why you can write order of 2 to the power n. Kishan,
Yes, sir.
are you there?
Yes, sir. Yes, sir.
So from the recurrence relation, we can derive the number of moves, and from the number of moves, we can derive the complexity of the tower of Hanoi. Is it clear to you?
Yes, sir.
Okay. So if n is equal to 3, then what is the number of moves? Number of moves is 7. Let us try with the program. So this is the Quicksort program. I'm just commenting the portion. Move. Void move. So start. This is the program. So void move, first argument in, that next is source, destination, and auxiliary. If the number of disk is 1, then just move from source to destination, just this line. Otherwise, there will be 3 steps. So first step will contain the complex time t of n minus 1. So t of n minus 1 from the source to the auxiliary. Please maintain the sequence. From the first move, you have to move the source to auxiliary using the destination as the auxiliary. Then in the second move, from source, that is the largest disk is placed from source to actual destination using the auxiliary. And the third step, third move the n minus 1 from the auxiliary to the destination using the source. Okay. So this is the call of move. Now we have to run this one. So number of disk, here number of disk is 3. Okay. So A to C, 1, 2, 3, 4, 5, 6, 7. So there are 7 moves. Okay. So 2 to the power n minus 1. 2 to the power n minus 1 number of moves are required. Is it clear? Is it clear to you?
Yes, sir.
Now first move, A to C. So you have to move from A to C. So first move, you have to move the A to C. So the constraints are, there are 2 constraints. First one, every time you can move, every time you can move only 1 disk. And second constant is that every time the smaller radius disk is kept upon the larger radius disk. So first move the A to, what is the output? A to C. Okay. So A to C, the smaller disk is placed from A to C. Next, A to B, the medium disk is moved. So the medium disk is moved from A to B. Okay. Next one, C to B. Next one is C to B. Next one is C to B. And next move, A to C. So this is the second step. It takes only constant time. So A to C. Next one, B to A. B to A. So move this one. Next one, B to C. So from B to C. And last one, A to C. A to C. So for n number of disks, there will be 2 to the power n minus 1 number of iteration steps. So this is the details execution of Tower of Hanoi. Okay, is it clear?
Yes, sir.
Not getting any answer.
Yes, sir.
Yes, sir. Clear.
Okay. Now we have to evaluate the postfix. Postfix expression. Do you know what is the postfix expression? Any idea about the postfix expression?
So first we write the variables and then the operand.
Okay. So evaluation of postfix expression. Evaluation. So this is the Tower of Hanoi. This is the Quicksort. And last one is the evaluation of postfix expression. So postfix expression, let it start with 3 get questions. First one is 12, just 12, next is 7, d minus division 2, 1, 5 plus multiplication and finally addition. This is first one, 8, 2, 3, exponential division 2, 3 star plus 5, 1 and finally minus. Third one, 5, 2 multiplication 3, 4 plus 5, 2, 5, 2 multiplication plus. So what will be the output of the first one? No, Kishan, this is not 10, first one.
So please show the question.
This is the first question. Is it visible? The first one. What will be the output? Any idea? $15. Yes. Pankaj Horse, you are right. This is 15. So how to solve this kind of problem? So what is the algorithm? Your algorithm is, first you have to scan from left to right. Scan from left to right. Okay. If you are getting any operand, push it in the stack. So from left we are getting 12. Push 12. So push 12. Okay. Next one is 7 3, 7 followed by 3. So 7 followed by 3. Now this is minus. Okay, minus. So if you are getting a operator, then pop the top and immediate top, these two operands. You have to pop these two operands. Okay, so 7 minus 3. So 7 minus 3. So 7 minus 3, what is the output? 4. And you have to store this 4 result in the stack top. So what will be the stack top now? Your stack top now will be 4. Okay. Next one. Next one is division. So you are getting a division. So you have to pop the top. So top, what is the top? Top is 4 and just below the top is 12. So 12 divided by 4. 12 divided by 4. That is 3. So 12 is divided by 4. Okay. Next one. 215. So 3 is placed in this position. Next 2, next 1, next 5. Okay. 215. Plus and then multiplication. So plus. So plus means you have to pop the top. So this is the top and below the top. So 1 plus 5. 1 plus 5. 1 plus 5, that is 6. You have to store this 6 in the stack top. So store the 6. Store the 6 in the stack top. Okay. Store the 6 in the stack top. Now multiplication. So you have to pop the 6 and 2. So pop 6 and 2. So 6 into 2, that is 12. 12 is stored in the stack top. Next one is plus. So you are getting a operator, you have to pop the stack top and below the stack top. So 3 plus 12. 3 plus 12. So this is 15. 15 is stored in the stack top. This will be returned at the output. So stack top will be 15. Is it clear? Second one. Yes, second one is 80.
Sir,
No,
please
no,
show
no.
the question.
Second one. No, third one is 80. Second one? Yes, third one is 80. Yes.
Sir, question.
Okay, this is your homeworks, okay? Question number 2 and 3. Question number 2 and 3, these are your homeworks. So how to evaluate the postfix expression? Your algorithm? Your algorithm is, first of all, you have to scan from left to right. Okay, first step. If you are getting any operand, just push in the stack. Unless and until you are encountered with the operator. If you are getting operator, just pop 2 operands, top operand and just below the top operand. Okay, and either plus or minus, multiplication, division, depending upon the operator, perform the operations and store the result at the stack top. Okay, so this is the algorithm for evaluation of postfix. Okay, is it
Sir,
clear? Yes.
sir, the output can be negative.
Output can be negative.
Hmm.
if output can be negative, if it is minus, it depends upon your expression.
So in question number 2, I'm getting -2.
-2, yes. Hertz in question number 2. Just 1 second. Just 1 second. I am solving this. 1 second. 1 plus 2. Question number 2. So this is from 2007 gate. TAC 2007.
So can you show the question, Mohammed?
Yes, 1 second. A23 then is exponential division 2 3 star 2 3 star plus 5 1 star minus. So the top two elements of the stack after the first evaluated are. So what will be the output?
2,
So +2, not negative.
+2, not negative. Okay. It depends upon your expression.
Sir, in this case, it will be 2 to the power 3, na?
2 to the power, just 1 second. 2 to the power. Yes, 2 to the power 3.
Yes, sir.
2 to the power 3.
So top one पहले लेते हैं ना.
No. This will be 2 to the power 3. So output will be 2 to the power 3. Output will be 8. So 8. This 8 divided by that 8. So 1. Okay. Next 2 3. Multiply 2 3. That is 6.
6.
So 6. And here in the top in the stack there will be 1. So 1 plus 6. 1
7.
plus 6 7. 1 plus 6 7. And this is your 5. Okay. So 7 minus 5, that is 7 minus 5, that is 2. Positive 2. Megha, this is positive 2. Okay.
Yes, sir, I said +2.
Okay. So output of the first one 15. Output of the second one. Output of the third one?
80.
Yes. Output of the third one is 80. So these are the questions coming from GATE.